Alright guys, so as we move on through into Unit 2, we're going to talk about the history of the Earth. And of course, oceanography really isn't complete unless we do talk about this because with 75% of the globe being covered with water, it makes sense that the question is asked, where does this all come from and where did the water come from, which is a big deal because it's such a unique situation that we have. Alright, so the origin of the universe. It all starts about 14 billion years ago with the Big Bang Theory. Now, the interesting part about the Big Bang is that if you think about it for a minute, in space we have no air, there is no discernible oxygen or anything of this kind. So without that being the case, the Big Bang really wouldn't be a Big Bang at all. It would be just more of a big poof, I guess. There'd be no sound at all. So just because there's nothing. Alright, so the way this worked is, the Big Bang happened that everything from a very, almost 10 billion years ago, everything stopped for a very infinite, very tiny point. So everything around you, every atom, every piece of energy, everything you can imagine, or see or witness, or sometimes can't see, all began from this very small point. And that's what the theory of the Big Bang is telling us. So the birth of the solar system is what comes next. So if we have the Big Bang about 10 billion years, well, 14 billion years ago, our solar system starts to come about later. And it becomes basically a mass of leftover stuff from the Big Bang. You get gas, dust, rock, particles, and all this stuff starts to condense on itself because of gravity as it gets tighter and tighter towards the center. Which we think at the center of our solar system, well, we're not 100% sure, we think quite possibly is a black hole, which would have been a massive star that died at one point. And then begins the black hole, and everything else left over begins to swirl to become that solar system. All right, in cosmology, the big theory on how our solar system began was the nebular hypothesis. And this is that flat, disky looking thing that spins of all that dust and all the particles and gas as it begins getting tighter and tighter. And it condenses with gravity. As it forms, that pressure in the middle from gravity and all of the gas, mostly hydrogen, to the center begins to compress. And at some point it compresses so tightly that the hydrogen atoms that are there get knocked together, and they get so tight, and when they're tight they begin to ignite and become nuclear fission. Nuclear fusion, not fission, fusion. As they fuse together, they make new particles. The new particles going right down the table of element all the way to iron. But what happens is that stuff gets so tight, so packed, and fusion begins, we end up with the star. And that star ignites and begins the nuclear chain of reactions. Now the sun stays round because of gravity pushing in all directions and energy being generated at the same time. So when we see our star being round, it's basically just an equilibrium between gravity and the energy it's producing. All right, the nebula hypothesis talks about that gas cloud being in the middle, or a nebula. If you want to see a nebula, you go out at night, look at Orion and Orion's belt. The Orion's belt is another nebula. So this is how we have the theory develop, or the hypothesis develop, because we are able to actually see these things happening right now. And we know stars are actually born here. That's probably what happened with our star. All right, and you end up with these turbulent eddies that begin to collect. They're kind of like tornadoes, I guess. Or if you think of an eddy in a river, it's like a little whirlpool. And this happens with the gas as it begins to spin. All right, as it begins to spin, we start to see actually energy form, and that fusion begins to happen. All the dust collects from the outside that's left over, and it gradually begins to fall towards the center and build mass. All right, as a result, we end up with this flat disk that rotates and forms the matter in the center. As that happens, that star begins to collect all that extra stuff, and it collects all that different junk, if you will, to the inside. I like to think of this as a toilet bowl. If you flush a toilet bowl, it spins around. What goes down first? Most of the mass, right? Everything else stays to the outside for a while. So if you think about this with the protostar, it's very much a toilet bowl situation. All right, this is a false color image of a protostar. This is a star that was taken by Hubble and it gives us a picture of what this could be, how this could be occurring. This is taken in space, so the diameter of the disk is about 20 times larger than our entire solar system. So we're able to actually see this and take this picture. So this theory or this hypothesis is supported because we can actually see this happening right now. All right, and of course that forms the sun. The hydrogen atoms fuse to give helium, and then of course the energy. We can study the how all this happens and how the sun lives and dies its death, but that's astronomy, so we'll skip that here for the oceanography class. All right, developing gas begins to swirl. Here we go with the toilet bowl thing going around. On the outside, everything begins to go to the center and collect all these molecules. But on the stuff on the outside that doesn't end up in the star or with the protostar, we call them planetesimals. Those planetesimals are what we end up with this stuff collecting on, piling onto it. And we end up with protoplanets. So very similar process begins to happen with the spinning of the gases when it comes to like the gaseous planets in Jupiter, Saturn, Uranus, Neptune. All that happens with them just like our sun, but they're just not big enough to collect enough gas to become an actual star. The other stuff is the stuff towards the inside. It becomes the rocky planets, which would of course be like Mercury, Venus, Earth, and Mars. Okay, so we end up with those two different planets, which, by the way, those two planets, a rocky one, we call a terrestrial planet. The outer gassy ones, we call Jovians. All right, so this is the end of part one. I'm going to have you do a lab right now. The lab will give you a chance to see this disk form and how that matter does. It's kind of a toilet bowl lab, a little different. We'll do it in the lab, however. And then I'm going to have you start looking at trends in the solar system. Remember, this is all building up to the formation of the planet. All right, talk to you later.